Hello, this is Satish for explaining basic electrical engineering subject, which is in Savitribai Phule, Pune University for first year. Here is the unit number 5th, Introduction to Electric Machines. In that, in this video, we let us learn about single phase transformers, electric motors. So these points are we are going to cover in this video. So first topic is single phase transformer and construction. So as shown here in this figure, in this picture, there is a laminated core, magnetic core, which is of material of silicon material. Okay, and this vertical part of core is called as limb. Vertical part is called as limb. Here the winding, there are two windings. It's called first one is a primary winding, which is get excited by the single phase supply, and another one winding is connected to the load. Okay, here is a whole construction of core is called as yoke. Okay, this is a secondary winding. Here the flux is shown here. Flux started to induce in a primary winding and flow from primary winding to secondary winding via this core. Okay, so this core is a laminated magnetic core. We can consider here. So flux is transferred via magnetic core. Now the working principle and EMF equation. Okay, so what is the working principle of single phase transformer? Normally, the working principle of transformer is on the uh, one principle of Faraday's law on mutual induction. Okay, mutual induction working principle is here shown in this figure. You can see visible this figure. This is one winding, core winding, and one winding is get excited by AC voltage. Okay, and flux are surrounded it, and this surrounded flux is going to linkage with the another one secondary coil. Okay, so there is a voltage is induced in a second winding. Okay, we get the lamp here enabled, okay, by this voltage. So now here this is one core, single phase core is excited and is flux linkages through this two magnetic core, and plus secondary turns are get induced these fluxes. So this flux is get by this core, and is this secondary windings is excited due to primary winding. Okay, so this is a basic principle is mutual induction. Okay, now EMF equation. So how you are going to derive the EMF equation? This is a graphical representation of EMF flux, which is drawn through this core. Okay, this flux is a sine function. So because of this flux is generated by sine voltage, sinusoidal voltage. So the flux is also in a sine function. So fluxes start from the 0 and end up to the 360 degree. Okay, here is a maximum value phi m value. Okay, so according to now we start, and we start here the EMF voltage derivation in first or secondary windings. Okay, so here is a total period time. The complete one cycle is required to complete cycle is called as a total time period. Okay, So according to Faraday's law, the EMF induced due to change in flux, rate of change of flux, which is induces the EMF. So according to this Faraday's law, we write here E average is equal to d phi upon dt. Changing flux. Changing flux is here taken as a final flux minus EMF flux upon time required. It's a dt. Okay, change in time also. So now here is a here in graphical presentation voltage started from the zero. Okay, so initial flux is zero and final flux is considered this half and half cycle. If we consider here pi m, okay, the pi m is the final flux, just this way. Okay, just this portion, this trajectory we consider here up to pi m peak value and pi m minus 0 upon dt is required to up to this time. The time if you consider up to 180 degree, it is a t by 2. It is a t by 2 up to 180 degree. For the pi by 2 up to 90 degree, it will be t by 4. Okay, so dt is equal to t by 4. So by simplifying this, we get the 4 into pi m into f. F is the 1 upon t. 1 upon t is replaced by f. So this is the value of average value. If we consider form factor, if we multiply with the form factor, we get RMS value. E is equal to 1.11 into 4 into pi m into f. So the equation, final equation 4.44 pi m into f. So primary induced voltage E1 is equal to 4.44 pi m f and 1. Secondary induced voltage EMF voltage E2 is equal to 4.44 EMF f into N2. Okay. Now the parameters, another parameters of transformer is transformation ratio and ratings. So here is the transformation ratio is the defined as the ratio of EMF voltage of secondary to the EMF voltage to the primary. Okay, the number of turns in the secondary upon number of turns in the primary. Okay, terminal voltage of secondary upon terminal voltage on primary. And here is inverse that we consider the primary current upon secondary current. So here the K is the transformation ratio for step up transformer. N2 is greater than N1. Okay, for step down transformer N2 is less than N1. 1 to 1 transformer N2 is equal to N1. Correct. So the rating is it is the output given by the transformer at the rated voltage and rated frequency under the usual service condition without exceeding the standard limits of temperature rise. Okay, so as a normal condition, the transformer is operated serviced to the load properly without any kind of disturbances. So this rating, maximum capacity of transformer, is considered as a transformer rating. So this is a normal general. We can take a V1 upon V2 and kVA. This is the general rating of a transformers. So kVA rating is equal to V1 I1 upon 1000 is equal to V2 into I2 upon 1000. Okay. So if you know the kVA rating, you can calculate by this formula. Primary current I1 is equal to kVA into 1000 upon V1. I2 is equal to kVA into 1000 upon V2. Okay. So here one principle we can consider here the kVA at the primary side, the product of I1 into V1 is equal to product in the secondary side I2 into V2. This is a one kind of phenomena of transformer. Transform the power with the same power. Whatever you transfer the power in the primary, the same power is transferred to the secondary. Just a difference between the level voltage level. If you increase the voltage level V1, here I1 get decreased, and in V2 is increased and I2 get decreased. Product is same. Okay, both quantities are not same, but their product are become a same. So the balance condition that the power in the primary winding is equal to secondary winding. So here the types of the transformers. There are two types of transformers for the syllabus concern. The core type transformer is this. Okay, there is a primary winding and secondary winding. HV high voltage primary winding, LV low voltage winding is inner of the HV winding. Okay, inner side, and their core. Okay, core is surrounded by the winding in the core type transformer. Okay, it's shown there the core section of the. If you cut the transformer core type this, you get like this vision. Yoke is the core material. This is a LV winding, and this is a dashes line is HV winding. Now the second next further type is shell type transformer. There is the HV winding in middle portion. LV winding is there upper and down. Okay, so the here core is surrounded of winding. Core is surrounded winding. Winding is not surrounded by the core. Here winding is surrounded by the core. Okay, winding is surrounded by the core in a shell type, and core is surrounded by the winding in core type. Okay, so this is the LV winding, and here the core winding. This is a normal function. So this is a cross section area of shell type transformer. The uh, comparison of core and shell type transformer. Core type transformer is like this. There is a figure diagram. Figuratively, we can differentiate between them. Shell type transformer like this. Okay, this is a three limb in the shell type transformer. There are two limbs in the core type transformer. Okay, so magnetic fluxes are transformed from the through the core. Okay, so one magnetic path is there in this. This is one magnetic path. Okay, there is two magnetic paths are here. So the main winding path is started from this way. This core is travel. Okay, core is traveled by the flux. Here also core is traveled by this core is traveled by the flux. Okay, winding surrounded. Winding is surrounded. Cores. Okay, core is surround the winding. Correct. Winding core is surround the winding. Natural cooling is better. Here is a heat is generated through the as a property of current. Heat is generated through the windings. So natural cooling is required. So here better natural cooling is there. Natural cooling is poor. Here's winding are get packed. So there is no enters and ventilation is provided to the winding. The easy repair and maintenance is here. So difficult to repair and maintenance in the shell type transformer. Concentric and cylindrical winding, okay, in a core type transformer. Sandwich and this type winding in a shell type transformer. High voltage applications, okay, for distribution. High power applications in shell type transformers. So ideal and practical transformers, okay. So here is one we say here ideal transformer which is a no which have no ohmic resistance, no magnetic leakage, no core has a infinite permeability. Okay, there is a lot of fluxes are there. Okay, no losses in the ideal transformer, but in practically there are leakages. Okay, so ohmic resistances are there in a primary side. There are ohmic losses, and secondary side is also in ohmic losses. Magnetic leakages, in the magnetic leakages, core has a finite permeability. There is a limitation in the permeability as per the property of the material. Okay, so there is a some finite amount of core carrying a permeability. Then losses is there. Practical transformers. Okay, so practical transformer there are losses. There are two types of losses. Basically iron losses or core loss or constant loss. There are three names to the one loss. Okay, iron loss, core loss, and constant loss. Constant loss. Another one loss is a copper loss, winding loss, variable loss. So So here now basically we start with the core loss. What is a core loss? Core loss is occur in a core. Okay, first thing you have to keep, this is a core showing the core. Okay, and this is a variable loss shown in a winding. So copper and core loss, copper and winding loss, variable loss is occur in a windings. Okay, this is a loss, this is we have seen in detail. Okay, so the iron loss is depends on the voltage. Okay, iron loss is depends on the voltage. As a this is a hysteresis loss is there. Okay, so this is a portion shows the hysteresis loss. The area of this hysteresis curve is considered as a hysteresis loss, which is a power. In terms of power is mentioned here as a formula. Hysteresis loss pH is equal to kh bm upon raised to 1.6 f into v. V is volume, f is the frequency, watts in terms of power. Okay, this is the hysteresis power, sorry, hysteresis loss we are concerned. So here is B is depends on the voltage. So this power loss is also depends on the voltage. Next, ED current loss, ED loss. Okay, this is the ED loss. So the AC, so ED is circulating current is created, okay, on the surface of a magnetic surface. So as their core winding is there with to the magnetic material. So in the magnetic material surface there is a circulating current is created. So in the eddy current loss, eddy current loss is considered as a KE. It's a constant term. KE is constant term. Bm square F square T square thickness V volume watts. Okay. Again here B term is there. So this also the voltage depends on the value of voltage. So this loss, eddy current loss is depends on the voltage. So how you going to reduce the iron losses? So here the types of loops are here shown. Okay, so wide uh, we get the loops area in hard steel of hysteresis loop. There is a rubbed iron we get like this, and silicon steel we get a very smooth and very uh, low, very narrow width by this curve. So this silicon steel is very suitable for the hysteresis for minimizing the hysteresis losses. So we are using the silicon steel material. Okay, and here the lamination is provided. Why we go to laminate this core? Because of if we use a single core, then the eddy current loss will take place here. Okay, so if we replace this single core by the laminated core like this, so the current eddy current circulating current get a distributed, get a distracted. So by this way the resultant magnetic flux will get increased by the laminated core. Okay, by the help of laminated core, by the construction of a laminated core. So then next the type is copper loss. So these losses occur in a primary and secondary windings due to resistance of the primary and secondary winding. Only in one resistance is responsible for the copper losses. Okay. So and one thing is there I1 and I2, the primary current and secondary current. Okay. So primary current depends on the load current and excitation current and the constant current. Okay, so here I1 is also refer as a very greater angle if we consider in a step down transformer. Okay, as compared with the I2. Okay, so R1 R2 is the primary and secondary winding resistance. The total copper loss is I1 square into R1 plus I2 square into R2. This is total copper loss. Copper loss is a main we consider as this is portion, this term is in a primary winding and this term is in a secondary winding. Next term is efficiency. Transformer act efficiency. How efficient transformer, the formula is of efficiency is output power upon input power into 100. Okay, and output power upon output power plus losses is nothing but the input power. Okay, so the output power of the transformer is electrical power, active power in the secondary side. So V2 into I2 into cos phi upon the output is same, V2 into I2 into cos phi plus Pi. Pi is iron loss plus PCU is a copper loss. Okay, so this is a formula for the efficiency. So if you consider the total loss occur in the transformer is iron loss plus copper loss. Okay, in iron loss there are two losses, ED current loss, hysteresis loss. In copper loss there is a primary winding copper loss, secondary winding copper loss. So the way, if you consider the characteristics of the efficiency with respect to the load current, as load current increase, the efficiency also increase. So there is, as per the capacity they get the increased efficiency. Okay, so maximum efficiency, and when maximum efficiency will occur take place, if you consider that there is a constant loss. Okay, there is a constant loss Pi, and here variable loss get increased as load increase, here as output current is increased, so the copper loss also increase. So at the point where this variable copper loss is cross intersect to the constant loss, this point is trajectorily we consider as a projection to the maximum efficiency. So maximum efficiency is occur when iron loss is equal to copper loss. Okay, Pi is equal to PCU. This is a term is very important. So efficiency at different loading and different power factor. If you consider here, okay, this is a primary winding side, this is secondary winding side, this is a assembly of transformer which carry the copper loss and iron loss. So efficiency formula is like this. If you loaded a transformer halfly, there is a X fraction is considered as a percentage of loading. Okay, there is a partially percentage if you consider 100% loading capacity of transformer. If you consider 5%, if halfly percent, you just have to maintain here 0.5. If you consider as 75% loading, if you have to write only 0.75. There is a term, this is a proper formula which I have given here. You just take it, okay, x into V2 into I2 FL into cos phi upon x V2 into I2 FL is a full load, okay, full load current cos phi plus Pi in plus x square into PCU full load. Okay, this is the efficiency formula. Here we take a x term as a multiple of square, okay, terms of square. So PCU is equal to I square into R1 plus I2 square into R2. PCU full load. At full load, if you consider, so full load currents are very important. Okay, full load means full capacity, full terms of we can consider as a rating, kVA rating. Okay, so here x term if you consider 25%, so the efficiency at this point. Okay, then if you load at 50%, the efficiency is at this point. If you load the transformer at 80%, so efficiency at this maximum. If you 100% loaded, then efficiency get decreased. Why this show? Why the frequency get decreased? So there is a nominal we can consider the 20% loss portion. Okay, 20% loss portion will drop here, so efficiency get decreased here. If you loaded means the percentage. Okay, you cannot be cross the limitation of loading, limitation of the rating, kVA rating. If you cross it, your transformer get damaged. So regulation, next term is regulation. Regulation term is for the voltage. How the voltage is constantly delivered at the secondary side. Okay, so it's nothing but a percentage of regulation. The formula is like this: percent of regulation is equal to voltage at no load minus voltage at full load upon voltage at no load. Okay, means here, see here, the voltage drops is across the primary winding. Okay, after the EMF voltage E1, and voltage drop across the secondary winding after drop in V2. Okay, sorry, drop in the secondary winding, we get the V2 terminal voltage. V2 is a terminal voltage at the secondary side. So this V2 is a fine full load voltage we consider here, and E2 is a no load voltage. Okay, so as if you consider a no load voltage, V2 is equal to V2 is depends on E2 is bigger voltage minus I2 in this drop in this parameter component I2 plus Jx. V2 is equal to E2 minus 0. If you consider the current, there is a load, no load connection. The current is also known here. So the terminal voltage V2 is equal to induced secondary voltage. Okay, if you not load connected to the load, the no load is conditioned like this. So the regulation is 0. E2 minus V2. If these are same term, so the regulation for no load is 0. Okay, and it is a very good, best value regulation. Okay, so at the load, if you consider there is a load connected, this load connected to the secondary side, so drop is occurred in a primary in the secondary winding. So therefore, there will be drop, and there if you consider the regulation will be increased. If you higher value of regulation you consider, this is a bad value. Okay, this is not a good value of the regulation. As a good performance we consider as a very low value of regulation. Okay, so percent regulation, if you consider I2, as I2 is increased, so smoothly regulation also increase. Okay, then if you consider for the voltage, secondary side voltage for resistive load, okay, there is also slightly get drop here. Okay, for the resistance load, if you do load consider if you load connect inductive load like a motor, then very high drop will be after take place here. Then if you consider if you connect this capacitive load, then there is a excessive power will be take place. Excessive voltage terminal is considered as a capacitive load. Okay, so this term for regulation. DC machines, now here DC machines and construction. This is another one topic. Next second part is this. Okay, so for the cooling transformers, here the construction, if you consider basic DC machine. Okay, there is a four pole is are there. Okay, four N and S, N and S. Okay, this is pole function is to spread the fluxes through the air gap. This is the windings, field winding is around the core. Okay, the air gap is here. Then slots at the armature, this is portion is called as armature. On the armature there is a commutator, fixed term is commutator. Okay, the commutators collect the current. Okay, convert the mechanical current to rectifier by the commutator. This is the brushes made of the carbon material. Okay, then armature winding is this. These are the bar. Okay, slots keep keep the bar is considered as a this is windings. Okay, field winding is here, which is take a current and start to induce the fluxes through the air gap. Okay, spread the fluxes. Okay, create a magnetic field, and cross sectional view is here. Okay, this is a shaft. You consider shaft term is here. Okay, so this is a total view, proper view of DC machines. Okay, brushes term is there. Okay, and commutator like this, air gap, cooling air, fan is here, armature. Now here frame surrounded yoke, we consider as a yoke as a frame. Then field winding surround the poles, laminated field poles is there again. Okay, cross section here. Next, so in detail we going to discuss each part in the DC machine. So yoke is the outer frame of DC machine is called as a yoke. It is a stationary part. It is made of cast iron steel. It does not only provide mechanical strength to the whole assembly but also carries the magnetic field produced by field winding. Okay, for the small motor and yoke are made up of a cast iron, but for a large cast steel or rolled steel is useful. Poles and pole shoots. Okay, so this is pole and pole shoots. Okay, this is pole shoes part. This is pole. This pole, and there's a windings. Okay, pole shoes are joined to the yoke with the help of poles and or winding. Okay, they carry field winding and the pole shoes are fastened to them. Okay, cast steel or the cast iron material is used. Pole shoes serve two purposes. One is they support field winding coils and spread out the fluxes in air gap uniformly. So field winding there are usually made of the core copper winding. Okay, copper field winding is there like this. This is a supply terminal voltage. Take a field winding like this. And pole is generated here. Another pole this series. Then also here. Then next. Then n terminal. Okay, so they wound in such a way that when energized and they form alternate north and south pole. Okay, spool winding former wound and help placed on each poles and are connected in series. Then next armature core. Armature core is rotor of the DC machine. It is cylindrical in the shape. Okay, it is cylindrical in shape with a slot to carry armature windings. Okay, to carry armature winding. The armature is built up of a thin laminated circular steel. This for reducing eddy current losses. So armature core is made of silicon steel lamination which are insulated from each other by insulating varnish coating. These laminations are used to reduce the eddy current losses. It may be provided with the air duct. Air duct is there for the axial air flows for cooling purpose. Armature winding it is usually farmers would wound copper coil which rest in the armature slots. Okay, these armature slots. Now here armature we are going to consider. Okay, so armature conductors are insulated from the each other and also form the armature core. Armature winding can be wound by one of two methods: lap winding or wave winding. Okay, this lap winding is shown here. Lap means one winding is another one winding. They are lapped. Okay, overlap. We can say lapping here. Winding are overlapped. So number of parallel paths are always number of poles. Okay, number of parallel paths here is two. Number of poles are two. So number of parallel paths is also two. Okay, so large current, low voltage is suitable winding is lap winding. For large current, if you require large current and low voltage, then lap winding is very suitable. Then current rating maximum up to 500 ampere, greater than 500 ampere. Another one winding is a wave winding, like wave is concerned, like wave is there, so commutator is there. Windings are in the form of progressive wave. Number of parallel paths are always two. Here number of parallel paths is always two. Incoming and outgoing, only two. Nothing on other one. Okay. So number of brushes set are always two. So high voltage is suitable for high voltage and low current, which is less than 500 ampere. Commutator, in case of the DC motor, and the commutator is used to convert DC to AC. Okay, so physical connections to the armature winding is made through the commutator brush arrangement. The commutator helps in providing current to the armature conductors. The commutator consists of set of copper segments which are insulated from each other. The number of segments is equal to the number of armature coils. Each segments, okay, each segment is a commutator part, okay, each segment is a commutator is connected to the armature coil and the commutator is keyed to the shaft. Okay, keyed. There is a key joined to the shaft. This is a shaft. Okay. Now brushes. These are brushes. Okay, the brushes assembly. Brushes is stationary part. Okay, this is brushes holder. Stationary part. Brushes are usually made from the carbon or graphite. They are raised on the commutator segments and slide on the segment when the commutator rotates, keeps the physical contact to the collect or supply the current. Okay, so DC motor principles like this. What is DC motor principles? As per the Fleming's left hand rule, if you consider left hand motor, you have to consider left hand rule. Okay, so Fleming's left hand what tells the forefinger is indicate direction of field, middle finger indicate the direction of current, and thumb is indicate direction of force. Okay, left hand Fleming's left hand rule. Okay, so like this, if there are two quantities are there is a field is present and current is already we supplied to the motor, then automatically the force will be take place. Okay, so according to Fleming's left hand rule, the force is here exerted on the winding on the object which is carry the current and which is placed in the magnetic field. It is a start to rotate or start to movement. So the force is take place here. So this is a working principle of the DC motor. So this commutator is there, which is a take the current DC current and convert into sinusoidal current AC. So this is to the current is passes through the each and every bar of the commutator conductors, armature conductor, and this which is a place in a magnetic field. So it is a it will be start to move. It will be start to move as per the force as per the Lemming's left hand rule. So DC motors types are characteristics. These types, what are the types? There are two, one type is there in this slide shown here. Okay, DC shunt motor and its characteristics are there. In shunt motor, the shunt field winding is connected parallel with the armature winding. It's called as a shunt motor. Supply is there, DC supply provided to the two components, the armature component, armature IA current, and shunt component is there, shunt current is there through the shunt field. So voltage equation will form in this, there two loops are there. The V is equal to AB plus IA into RA. IA into RA is the armature drop. Okay, so as per the KVL, V supply voltage is equal to EB back EMF, which is the induced voltage in the EMF in the magnetic field in the we call that the sorry in the winding. Okay, back EMF will be generated in the armature. Torque relation, torque is here. Torque is directly proportional to pi Ia and Ia. Ia is the armature current. Speed relation N is directly proportional to back EMF upon phi, or EB is replaced by V minus IA into RA. Okay, so here is a first characteristics torque versus armature current. Torque is increased as the current is increased. Armature current get increased, the torque is also increased. Okay, then as you know the torque term is a twisting term. Okay, twisting force term is considered as a torque. Okay, next speed versus armature current. Speed of the DC motor is constant, ideally constant. There is no change in speed as of varying a load. The constant voltage, constant speed is provided by decision motor. So for the practical, if you consider some drop is occurring in the speed, okay, this dotted line is shown the no load speed. When your motor is not connected to the load, the motor is rotated at a constant rated speed. If you connect it to the load, some drop is occur here. So there is a smoothly sliding line is shown here. So the speed versus armature torque is same. Okay, same we consider like this. Next type is DC series motor. The shunt series field winding. Field winding is connected series with the armature winding. It's called as DC series motor. Supply is there provided. Positive DC supply is provided here. So voltage equation is like this: V is equal to EB plus IA into the summation of resistances RA, armature resistance, plus say series winding, field winding resistance. Here torque is proportional to phi into I. Here phi is gradually more, so the armature current is more, so we consider as phi Ia square. So speed relation in the DC series motor is like this, same. Similarly, we can consider the EB upon phi. So EB is replaced by this term, okay, by this KVL equation. So V minus Ia into in bracket RA plus RAC upon IA. Okay, so now let us understand about the about characteristics. Okay, torque versus armature current. As the current armature current is increased here, torque is gradually enhanced here like this. Okay, torque is not directly proportional to the Ia. It is proportional to the I square. Okay, square term of I as increased, the torque is increased. Then speed versus armature current. Initially, see, DC series motor is at a high speed, so it is start from this way. So as you increase the load, as you increase the current, okay, so speed get decreased more and more here. So similar way we can consider as this the speed versus armature torque. If you increase the armature torque, the speed get decrease. Okay, this is a characteristic of DC series motor. The application DC series shunt is here provided. DC shunt applications is fans, centrifugal pumps, lathe machine, drill machine, milling machine, blowers, machines, tools. Okay, DC series motors is used for the elevators, electric traction, locomotive, troll. There is a high starting torque is there. No load condition not possible. Okay, not possible variable speeds. Motoring starting constant speed starting we consider as a DC series motor. Now next motor is a three-phase induction motor. Advantages: the three-phase induction motor is our most common and frequently used machines in the industries. Simple design, rugged, low price, is easy maintenance, wide range of power rating like fractional HP to the 10 megawatt. So run easily, essentially as a constant speed from the zero to full load. Okay, reversed, no brushes, no any contact on the rotor shaft, squirrel gauge. High power per weight ratio is there compared to DC motor. Low power, low cost per power. Speed frequent frequency is dependent. Speed is frequency dependent. We can let us see that. So there is stator and rotor in the three-phase machine. Okay, there is three-phase RYB is there. We consider this is a stator part. Okay, and stator winding is terms of delta. Stator winding connected in delta. So this is core. This is rotor part. Okay, this is shaft short circuited rotor part. This is rotor bar. Sorry, it's short circuited. Okay, shaft is there. The whole assembly like this. If you consider there are winding connections to the rotor part, there slip rings are provided. Okay, so like these slip rings are there. If you consider rotor connections, rotors are there in a star connected, stator is in a delta connected. Okay, so we can take a connection. This is shaft, slip rings are there. The shaft, so slip rings is connected with the brushes. So external star connected rheostat is for the maintaining speeds, controlling speed of the machine. So the working principle of a three-phase motor. So as per we consider the left-hand rule is there, that is law of induction. So there is force is exerted on the each and bar of the rotor conductor. So there is a three-phase supply provided and air inner fluxes are produced in a air gap. So fluxes is there, yes, and north pole is current here generated. So here current we also provided to the rotor. So the N pole is here. If you consider N pole is at the here we consider dot as a current direction, okay, towards the observer, and cross is current direction away from the observer. So here the current force is there, fluxes from the direction. So fluxes as the relative flux is created here. So motor start to rotate. Relative fluxes, relative speed is is here take place. Relative speed is that like the rotor speed, okay, is reaching start to reach towards the synchronous speed. Okay, there is a difference between a synchronous speed and a rotor speed is called a relative speed. So there is a rotor fluxes due to the induced rotor current is like this. Okay, so the rotor is start to catch up the synchronous speed. Synchronous speed is a flux speed. Okay, synchronous speed is a filter speed. Okay, in which is a present in a air gap. You get that? Okay, so this is normally direction shown the direction of the motor. How like this? So as the direction of synchronous speed, the direction of rotor is there. Okay, if the direction of synchronous speed is in a clockwise direction, so rotor also rotate in a clockwise direction. Okay, so there is a comparison. There are two types of motors of three-phase motors. Induction motor. There is a squirrel gauge and slip ring. The comparison is there. So construction is simple in a squirrel gauge, and in a slip ring it is complicated. Rotor bars are made of aluminium. Here the motor three-phase winding is linked like to status. Okay. End and slip ring there is no circular short circuited, so there is not provided in a squirrel gauge. The slip rings windings are connected to slip ring motors. External rheostat there is a not any kind not able to connect external resistors in the squirrel gauge. Here is a provision. Here is a scope for the connect the external resistances. So external resistance can be added in a rotor circuit to limiting the starting current as well as increase the torque. Starting torque lowering here in a squirrel gauge, lowering lower starting torque compared to the wound rotor. So the higher starting torque is available in the slip ring. The speed control using rotor resistance is not possible as the rotor bars is short circuited. Here is easier speed control by varying the external resistance connected to the rotor winding. Efficiency in a squirrel gauge, higher efficiency under the normal operating conditions. In a slip ring, lower efficiency due to additional losses in a external resistance or brushes. So high maintenance free as no there is brushes, no slip ring. There is maintenance required in a slip ring. So cost, if you consider cost, is lower of squirrel gauge and higher in a slip ring. Application, similar application if you consider, the squirrel gauge is used for lathe machine, drill machine, then moderating starting torque and constant speed, high starting torque, variable speed. Single phase induction motor. single phase induction motor is remains one of the most widely used motors for a domestic commercial or small industries application where only single phase power is available. Okay, in our home there is fan, mixer, fridge, refrigerator. There are small motors which is operated on a single phase. Okay, 230 volt. Single phase induction motors stand out as one of the most common essential devices. Simple, easy to build, robust, low cost, and maintenance. So there is a construction, similar construction we can consider like this. Okay, the fan cover like this, cooling fan, end end bell is like this. Then wiring box. Okay, for single phase we consider the single phase and neutral. Lift tie. Okay, so we have to lift here. Nameplate is here. Nameplate. The information of motor is provided on the nameplate. Stator windings, bearings are there. Okay, squirrel gauge, bearing, bell bearing is there. Now the stator and stator winding. Okay, as the name indicates, it is a stationary part of the induction motor. So made of silicon steel strips of the thickness varying a zero point 0.3 to 1.35 mm. These strips are combined, which are called laminated strips, and the combination is known as a laminated form. These laminated stamping strips are slotted to receive winding. The stator core is laminated to reduce the eddy current losses. In a single phase induction motor, there are two windings made of the coppers and are used in a stator. Out of these two windings, one winding is main winding and second winding is auxiliary winding. There are two windings. Okay, so this is a single phase motor is not able to start on one phase. We require to split the phase. Okay, so we create a auxiliary winding, two windings. One is the auxiliary winding and one is the main winding. Okay, so for auxiliary winding is required for this to start the motor only. We use it for only start purpose. Okay, initially if the motor is take a twisting to keep the start and take a torque, then we remove the auxiliary winding. Okay, so the rotor, your rotor the description is there. Rotor is a rotating part of the motor and made of the silicon steel strips. The thickness of these strips it varies from zero point 0.3 to 1.35 mm as the case of the stator. These strips are clamped together to form the rotor core called laminated core. This laminated core is slotted totally close to the closed type to receive the rotor winding. In large capacity motors, sticks aluminum bars are inserted and are short circuited with the end rings. Nowadays, the melted aluminum is filled in this slot which works as a short circuited winding. This winding is known as a squirrel gauge winding and the rotor bar is brassed to end ring to increase mechanical strength of the motors. Okay. Now centrifugal fugal switch, as the name indicates, it is a switch. So which switch are on the switches of on principle of centrifugal forces. Okay. So the centrifugal force set rotor set to rotating. Okay. So when the motor is standstill position, the switch contacts remain closed. Keep the starting pointing to a circuit. So cut off starting winding out of the circuit. The motor attains more than 80% degree rated speed. So when the motor is switched off, the starting winding is again inserted into the circuit by switching on the centrifugal. Okay, the centrifugal assembly is there. Okay, switch is this light. Okay, as the motor reach up to 80%, it will be disconnect the auxiliary winding. So working principles is like this. That is law of electromagnetic induction. So as AC supply given to the stator winding, which is single phase, the current flowing through the windings produces magnetic field, which is called the stator magnetic field, similar as it is. Okay, the EMF is also generated, so pulsating pulses. So acting as external squirrel cage, rotor cannot produce rotation. Okay, therefore the single phase we not call as we cannot say it is a single self starting motor. Okay, so these are things are there. So positive stable main winding and start winding we require, and there is a space of 90 degrees distance apart is difference is required to start the motor. So hence we have like a two wire phase motors. Starter produces revolving magnetic field which causes the rotor to run. Once a motor gathered speed 80% to 90% is normal. Okay, the starting winding gets disconnected from the circuit by means of centrifugal switch, and the motor runs only one main winding. Okay, starting winding is considered as the auxiliary winding. Okay, like this. So this is shown here. So motor get, so the disconnection is occurred. Motor get a speed up to 80% or 90% as per the design. The switch get opens and it's disconnect the auxiliary winding. So application like this, split phase motor is there. Split phase motor, there are two phases are created here. Split phase motor. So the application is like this. Starting winding shows starting torque is shown here. So resistance start here, resistance start we call as a resistance start induction motor, about 1.5 times full load torque. The maximum full out torque is about 2.5 times of full load. Washing machine, air conditioner, food mixers, grinders, floor polishers, blowers, centrifugal pumps, small drills, lathes, office machineries, we require split phase induction motor. Capacitor start motor is there. The capacitor is required in auxiliary winding we use for the starting purpose. So by help of this, we get a more torque. Okay, so developing high torque, about 3 to 4.5 times of full load torque. Okay, for starting purpose. So to obtain the starting value, starting high torque value, the starting capacitor must be large and resistance starting torque must be low. So electrolyte capacitors order of 250 microfarad is used. Application is like this: pumps, compressor, conveyors. Okay. Then capacitor start and run capacitor run motor is there. The main advantage of these types of connection is to improve power factor. So used to load higher inertia, requires of frequency, using pump equipments, using refrigerators, air compressor, we require a fixed capacitor. Okay, so at 80% speed, this starting capacitor get disconnected because of centrifugal switch, but this capacitor remain in the circuit for the run purpose for maintaining the power factor. Permanent split capacitor PSIC. Okay, so as only one capacitor is connected in the series continually, this permanent capacitor is with a starting winding, and the capacitor is permanently connected. Okay, no centrifugal switch is required. So as a high efficiency, higher power factor because of permanent connected capacitor, low starting torque, paper phase or oil filled type of capacitor are used. So used for the fans, blowers, in heaters, used in air conditioner, used in drive refrigerator compressor, used in operate office machinery, ceiling fans. Okay. So thank you for watching this content for, and please share and subscribe, like to video. Thank you.